Hey guys, today I want to show you what are the applications in terms of math of the intermediate value theorem. It's pretty cool, so let's dive into it. So now, one of the applications that the intermediate value theorem has is to prove there is a solution to an equation. For example, if we have this equation is annoying to solve. So before you start actually trying to find the solution, one thing you could do is to make sure there is a solution. And you could do that with the intermediate value theorem. Let me show you. So what we need to show, first of all, is that this is a function. So we're going to define f of x as x cubed plus 2x. And we need to prove that there is an n value or whatever that's such that f of n is equal to 6. And now one way we can do that is, first of all, by plotting this function f of x. So we would have a graph. And of course, yeah, you can have some negative quadrants. And you have your inputs and f of x. So we can do what we can do first is to find some points in this graph. So let's define first of all how much f of 1 is. So if we have f of 1, that's going to be equal to 1 cubed plus that's just going to be 3. What? Yeah, 1, 3, yeah, 3. It's going to be 3. Now let's define a second point. That's just going to be f of 2. And that should be equal to 8, 12. Now in this case, we have 2 points that we can plot here. So I'm going to say that in this case, we've got 1, and over here, we've got 2. And I'm going to say that, for example, maybe this is a polynomial, a third degree polynomial, so you don't have a parabola. So maybe some squiggly line. First of all, I'm going to say this goes here, probably this goes up here. So you would go maybe like this, and then probably like this. Yeah, this is kind of that's maybe way too squiggly. So maybe make it a bit like this, something like this probably. Yeah, that works. So now we know we've got two points. And we need to show that between those 2 points, which should be actually, it should be actually a bit bigger, because that is 12 and that is 3. Let's say actually that point is here. Yeah, now it works, yeah. So we have 2 inputs. We have 1 and 2. And we know 1 corresponds to the output 3. So we should have 3 in here. And then we know 2 goes to 12. So we should have 12 in here. If you think about it, we know, because this function is continuous at every point, we know there is a value between 3 and 12 such that its input had to be a number between 1 and 2. Does that make sense? That is the entire intermediate value theorem. We know that between 3 and 12 lies 6. And we got these values, 3 and 12, with 1 and 2, which means that there is a value between 1 and 2, which I'm going to call C, that should complete this condition. C is going to be greater than 1, it cannot be equal actually, greater than 1, but smaller than 2, such that, such that f of C equals 6, okay? This is the entire proof that there is an actual solution to this equation. We're basically stating that between these points, in this interval, there is an x value that you can plug in, and you're gonna get a value that is 6 between these two, between this region of the y values, okay? And this is one of the applications of the intermediate value theorem. You can prove for complicated equations that there is an actual solution that, well, your effort might be valuable in order to find it, okay? You're not doing nothing. At least you know there is a solution that you can find. So this is one of the applications of the theorem. So I hope you guys enjoyed this video, and see you in the following one.